Hello friend, I am Ghanshyam and welcome to today's lecture. And today we have to study about the power system fault analysis. So previously we have discussed the how to transmit electric power and distribute electric power in the topic of structure of the power system. And today's topic is our fault analysis. So how to detect fault and what are the type of fault occurred in the power transmission that are discussed in this video. Okay, so what is fault? Fault is the abnormal situation of the current flowing or voltage exceeding beyond the limit. Okay, so a fault in a circuit is a failure that interferes with the normal flow of current. Okay, if there is a normal flow of current, if the magnitude of the current is exceed beyond this limit, the current will be exceed, then it will be called as a fault. Okay, so a short circuit fault occur when the insulation of the system falls, resulting into low impedance path. So if current will be increased, when current is increased, then impedance will be decreased or resistance will be decreased. So when impedance or resistance is lower or decrease or smaller, then our current will be very high. So it is called as a short circuit fault again. And fault resulting in the impedance path either between phase or phase to ground. And this causes excessive high current to flow in the circuit, requiring the operation of the protection equipment to prevent the damage of the equipment. So there are two type of fault. There are two type of fault, like symmetrical fault and asymmetrical fault. So before going to our all those symmetrical and unsymmetrical fault, let us know the brief idea of what is symmetrical fault. So there is a three phase in our system. We know already three phase. It may be two phase, it may be one phase. We may basically take in the three phase system because of the three phase system have our vast network, so it require more discussion about this. So three phase system and fault caused by the application of three equal fault. So a symmetrical fault occur when three equal fault occur, or three equal fault in the equal impedance Z fault. Impedance of fault impedance, that is fault impedance, is equal to 0. That means the current in the three circuit will be very high. Okay, the fault is called the solid or vaulted fault. This fault is called a solid or vaulted fault. Okay, remember that two things. So those fault can be two type. One is a line to line fault. Another one is line to line to line to ground fault. Okay, those are the two type of symmetrical fault. So in the next slide we have see the two fault. This is our line to line to ground fault. Okay, those are three line. Let it is a phase A and phase B, phase C. Those are three line with respect to ground. Fault occur here when three line are contact each other or contact at a point and it is fall on the ground, then it is called line to ground fault or symmetrical fault. Or when three phase are connected with a point, with a common point, then this fault is called a symmetrical fault or line to line fault. Those are our fault impedance. Okay, Those are our fault impedance. So the line to line LLL fault and the line to line to ground, those fault are basically our own symmetrical or own balance fault. Sorry, this is our symmetrical or balance fault. It is not our unsymmetrical fault. Okay, the behavior of triple LG and triple L fault identical due to balance nature of the fault. This is our balance nature of fault. Okay, it is not unbalanced. It is a balanced symmetrical fault. Nature of the fault. If the ZF is equal to 0, this fault is usually the most severe fault. Okay, it is most severe fault and it could not happen every time in the power system network. Then come to our asymmetrical fault. Unsymmetrical or asymmetrical or unbalanced fault. So here is the figure showing the unsymmetrical fault in which balance state of network is disturbed are called the unsymmetrical fault or unbalanced fault. It may also called unbalanced fault. Unbalanced fault. The most common type of unbalanced fault in the system, single line to ground fault. This is single line to ground fault, and line to line opening fault, and double line fault, line to line fault, and line to ground fault. Okay, those are the three type of our unsymmetrical fault, and this is most severe, not severe, this is not severe. Those are the line to ground fault occur 60 to 75% in our power system, and line to ground and line to line fault are occur. Those two fault, line to ground and line to line fault, occur 15 to 25%. Now only line to line fault occur in 15 to 12%, 8 to 25%, and line to ground occur 5 to 15%. Remember that. Okay, this line to ground occur 5 to 15%, and line to line fault occur 15 to 25%, and line to ground fault occur 60 to 75%. So mostly our line to ground fault occur in the power system. And we have discussed further those unsymmetrical and symmetrical fault with its description, with its mathematical derivation in the later chapter. So today we have discussed only the basic part of the symmetrical unsymmetrical fault. So going to next slide, the symmetrical or balanced three-phase fault. This is our single line symmetrical or balanced three-phase fault diagram. This is our generating station, this is our power transformer, this is our bus bar, and this is our load with another bus bar here with another load. This is our making breaking circuit with this is our fault impedance with a fault current with voltage, and it is connected with ground. Okay, it is clear. I think it is clear to you. Okay, so let's see, as the symmetrical fault is analyzed on the four-phase basis. Here two phase carry identical current but with the phase shift with 180 degree. Because of there is three phase na, one is phase red, another one is Y yellow, another one is blue, so it is 120 degree apart from each other. All those three angle 120 degree apart from each other. So phase shift of 180 degree. A fault in the network is simulated by connecting impedance in the network. This is our impedance. It is the fault location. And the faulted equivalent network is seen from the fault point. The Bose impedance matrix is convenient to use. Later on we have to discuss our matrix form of the impedance, Bose impedance. Okay. And a typical Bose of n bus power system network is here or in the next slide here. This is a typical n bus network. Further, a balanced three-phase fault through a fault impedance of ZF. This is our fault impedance ZF is assumed to occur in the kth bus. It is our kth bus. Okay, this is our kth bus with k voltage, initial voltage. This is our initial kth voltage. Okay, bus is shown in the figure. Pre-fault load flow provide the information about the pre-fault bus voltage. So this is also called as our pre-fault voltage. Pre-fault voltage, this VK0 voltage vector, and this vector pre-phase voltage vector is equal to, let me write here, V10 dot 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 VK0 dot 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 2 VN0 transpose in the per unit. Okay, remember that in per unit. The fault in the kth bus through an impedance of ZF will cause in change in voltage, changing the voltage of the bus del V bus. That is, change in voltage is equal to that pulse del V bus due to the flow of heavy current through the transmission line. This change can be calculated by applying voltage VK0 at kth bus and short circuiting all other the voltage sources. The sources and the load are replaced by their equivalent impedance. So let me erase first here. Now here is ZK impedance. Where it come? ZK are the equivalent load impedance of ith and kth respectively. Okay, it is the equivalent load impedance, and ZIK is the impedance line between ith ZIK is the impedance line between ith and kth buses, and here is xth. Okay, xth is the appropriate generator reactance with Zi, ith bus impedance. The fault current VK0 is the pre-fault voltage at kth bus from the superposition theorem. The bus voltage due to fault can be obtained as the sum of pre-fault voltage and the change in the voltage due to fault. So let me erase first. So here is V was fault is equal to pre-fault voltage V was 0 plus change in the voltage when fault is occur, that is del V was. Please write it on your paper. That is V was fault is equal to V pre-fault voltage plus change in voltage when fault occur. Okay, take it as a equation 1. Then coming to next slide, where V was at the fault is the vector of Volt's voltage during fault is equal to V1 fault to Vi fault to Vn fault with its transposition, and then V was 0 is the vector per fault pre-fault bus voltage. Those are here. And V was fault, del V was fault, that is change, vector change in the bus voltage due to fault, V1 bar to Vk bar to Vn bar transposition. Also bus injected voltage IV bus is equal to Y bus into V bus, because of I is equal to V by R and 1 by R is equal to Y. So V into Y, that is V into Y is equal to I. Okay, so here V bus is the bus voltage vector and Y bus is the bus admittance matrix. With all the bus current, expect the faulted bus K equal to 0. If K is equal to 0, the node equation of the network figure shown in here. So this is our matrix form. It is saying except kth bus all entry are 0, then what is the matrix form? This is our I is equal to Y into V, so that V is equal to V1 V2 del Vk to del Vn and Y11 Y12. This is our matrix, and this is our diagonal matrix Y11 Y12 Y22 Y33 Y44 YKK Y2 YNN, like that. Okay, so as per the fault current, IK fault is leaving the bus. Let me show to you here. IK fault is leaving in this direction. Leaving the bus is taken as a negative. It is taken as a negative current entering the bus. Hence, I bus is equal to Y bus into del bus. I bus is equal to Y bus into del V bus. Okay, so del V bus can be calculated as, now let me erase. So del V bus is equal to Y bus inverse I bus fault. How? Because of the I is equal to V into I na, V into Y na. So V bus is equal to this Y will be converted to its denominator, and this denominator will be transferred to inverse form. Okay, so here let me erase. where Z bus is the bus impedance of the matrix and V bus inverse. Substituting the expression of del V bus from the equation number 2, whatever we have calculated in the previous equation, that equation. In the equation 1 can be written as, here let me write here, V bus fault is equal to V preferred voltage V bus 0 plus Z bus fault into I current bus fault. Okay, so expanding the above equation, we can write, expanding that above equation, we can written here it is gone. This is our form. So by putting the equation number 2 in the previous and equation number 1, we can get that V1 fault is V1 fault, V2 fault, V3 Vk fault, Vn fault is equal to V1 0 pre-fault voltage, and this is our impedance at the fault, and this is our current at the fault bus. Okay, so here at the bus KTH voltage is expressed as a I'm written here Vk fault is equal to Vk0 minus Zkk into Ikk. Okay, Vk fault is equal to Vk0 minus Zkk into Ikk. And also from the figure, Vk fault is equal to Z fault into Ik fault. So Ik fault is equal to Vk0 divided by Zkk. But it's Ohm's law only, no? You have known the Ohm's law already. That's why I am not telling you about that. So Ik fault is equal to Vk0 divided by Zkk plus we are taking Z fault. Why? For the faulty with non-zero fault impedance Zf. If we are not taking that Zf is not equal to 0, then this is our formula. And in this, the quantity of Zkk in equation number, that equation, Ik fault is equal to Vk0 divided by Zkk 2 plus Zf is the Thevenin's impedance of the open circuit impedance of the network as seen from the voltage faulted bus K. So here we can write Vi fault is equal to Vi0 minus Zik into Ik fault for all I is equal to 1 to n and I is not is equal to k. Substituting IKF from the equation this, and VIF can be expressed as VIF is equal to Vi0 minus Zik divided by Zkk plus Zf into Vk0. The fault current Iij fault flowing through the connecting it and JTH bus can be calculated as Zij fault is equal to Vf minus Vjf divided by Zij, where Zi is the impedance between the I and J. Okay, it is clear to you, I think. So on the upcoming video we have to discuss our line to ground fault and line to line fault, line to triple line fault, triple line to ground fault, all those faults in detailed manner with its mathematical derivation. And for today's lecture it's okay. So for watching, thank you.